All right, chapter 8 starts something called exponential functions and logarithmic functions. We'll see what's the whole point here, but if you think about it, ever since all the way back in chapter 1, what we've done is we've looked at linear functions in chapter 1. In chapter 2, we looked at quadratic functions. And so far, all this time in Mathematics 3, we've been sort of looking at different functions along the way. Name me a few more here. Something called rational functions. Remember those fractions? That was chapter 5. And then remember all the square root stuff that we did. Those are called radical functions. And finally, we come to the tail end, the last two functions. They always go together in each of the chapters in algebra because there's a link there. So exponential functions and logarithmic functions here. Okay, as already stated here, you do need a calculator. You need a scientific calculator, something that has a log button and an ln button somewhere on there. And again, even most scientific calculators that you download would have those. So if you want to download a calculator, that's cool. All right, but what's this whole idea of exponential functions in the first place? Exponential functions are multipliers to something we've already had before. So a good example is bounce of a ball. Ever notice a bounce of a ball goes like this? It goes lower and lower and lower. And so the height, maybe from the way it's dropped, is h. The second bounce is going to be 2/3 of the previous bounce. And then this one's going to be 2/3 of the previous bounce. And then this one's going to be the height 2/3 of the... So notice it's like a multiplier. 2/3 times 2/3. So if you multiply this one, this will be 4/9 of this bounce. And then multiplying another 2/3, what would that be? 8/27, is that right? Of the original bounce. All right, so and you can calculate it, of course. So there it is. There's 2/3, and then you have, hey, look at that. Instead of putting another 2/3, another 2/3, another 2/3, can't we just do this here? Put exponents here. So the third bounce really is, I'm taking 2/3 to the third power. Fourth bounce, the height of the fourth bounce would be 2/3 taken to the fourth power. So then the question is, if I'm looking for the nth bounce, hey, that's okay. The pattern is here. It is 2/3 to the nth exponent. Kind of cool. I think that's cool. The fact that we can figure out exponential growth. All right, but let's go practice just a little bit here. And I should have warned you last time that you probably needed a calculator. So if you can sort of find one, if not, then we're going to use it throughout the chapter here. And of course the next question comes up is, Mr. H, are we going to use a calculator for the exam? Of course not. Because all the problems on the exam will be non-calculator based. So concentrate on the ones that you don't need a calculator for. All right, definition, of course. Definition is an exponential function is any number, as we saw earlier, with a base and then to a certain exponent. And the exponent is our variable. So that's what we're going to change. We're going to change that x into a whole bunch of different things. All right, and if you download it and print it off the match problems, you find out for number 1, at least that you guys agree. If you guys disagree here, there's a A, the B is missing, then there's a D, and then the C is missing. Is that right? Just kind of check, make sure I didn't print out the wrong one. Okay, so let's go for it. So f of x is equal to 4 to the x. And if you say f of 0, what you really mean is you're putting in a 0 in for the exponent. Anybody 4 to the 0 power is? Yeah, it's always a debate, you know, like half the class says 0, and then half the class says 1, and then there's a big old feud. No, it's just 1. So any number to the 0 power is 1. We saw that when we were doing exponent rules. Chapter 5, chapter 6, I think it was chapter 6. Okay, f of 3 means 4 to the third power, and that one you do have to calculate a few things here. So 4 times 4 times 4. 64 is good by me. Yep. Again, don't need your calculator for this. We'll do some other stuff that needs a calculator. And bless you. All right, C and F. Oh, the E is missing. There you go. A, B, and E. Alright, so again this would be 4 to the second power, and I think we all know that one to be 16. And then we have this little negative in there. I think we already know what happens with negative exponents, right? If you see a negative exponent, where does the 4 go? Too early in the morning, I understand. Denominator, you got it. This now is in the numerator now. It's going to go to the denominator. And then still doing some more work gets you 1/16. Alright, I like this chapter because there's plenty of application questions. Exponential functions, we use them in business applications. There's a whole class that I've seen. It's all about interest and something called annuities and percentages. How much money will you have when? And there's a whole class devoted to that. If you ever had a life insurance person come over to your house selling you life insurance, they'll flip their laptop up and it's okay. If you put in this much, you get this much when you're 70, if you live to 70. So this whole concept of money growing as it as the years progress here. So a lot of applications like that, especially the exponential functions here. So this one, it is inside your textbook here, and the match problems don't tell you what this actually is. Let me see if I can get it. This is concentration of iodine in a person's blood for a certain amount of days after you've taken a 1,200 microdosage of it. So again, just kind of where it comes from. What we're interested in is, can we just work with the numbers? Now this one, yes, this one does require a calculator to finish up because you cannot do this in your head, not like the previous ones here. So let's go with it here. So a of t is equal to that function here, so a of 12. If you do that, and this is what they want you to sort of see, is there's no way to plug that in your mind. Look at this. So you got 1200 times t, which now is 12, to the negative looks like 12 over 8. And we have to reduce that a little bit here. You can keep the exponent as a fraction, that's fine. I would probably go change it to a decimal. Just see what that's going to give you. So 1200 times 12, and then that reduced would be 1.5, right? Let's see, it'll reduce by 4, it'll be 3 over 2. Okay, this is what I want you guys to understand here. Can you do this in your head? There's no way to take a exponent of negative 1.5, or like half an exponent. Doesn't make sense. At this point, your calculator, in a sense, has to help you out. Cool. So punching that in, all yours, go for it. And I'll give you what I punched in, and then we'll see if we get the same thing here. Alright, and this is what I plugged in here, so 1200 times 12 to the taken to the exponent of negative 1.5, and we get ourselves approximately 28.9 or so. Okay, why the highlight on the answer is because the answer at the end of the match problems, that's wrong. I don't know what they got. Someone was not paying attention, or they plugged it in wrong here. Okay, so 28.9 approximately. Sometimes when the answer's in the back of the book, they might actually leave it as like 28.87. I mean, if you're close enough, you're fine, because the answers, the directions on the homework doesn't tell you how many decimal places you need to have. Cool, so as long as you're right there. On the test, of course, I'm not going to have like, oh, 28.8 or 28.9. It's not going to happen. And this problem is not going to go show up on a test either, because it's a calculator question. Okay, next problem. Actually, no, before we go on, quick here, raise your hand. How many got that on your calculator? All right, hands down. How many tried it on your calculator and still didn't get it? 1, 2, 3, 4. Okay. Let me do this here. Let's do the next problem, and I'm going to come by and I'm sort of going to help you guys to get the first problem and the second problem here. So all yours, those that got it here, 24 plugged in now. So 24 is the base, negative 24 over 8. And just to sort of show you, this one you actually could do by yourself, right? Because it's actually an integer exponent. Okay, let me just sort of walk down here. Okay, skip to be first here. So last problem. I just didn't know. Let's be careful. The power. Just want to make sure you can get it. For the second one? For this one? This one? Yes. I think so. Let me give you the answer here, and I'll walk around the room here to help you in case you didn't get it here. All right, so that's the more like the evaluation of exponential functions here. So let's jump to now the graphing aspect of them. What do they look like? We know what parabolas look like, but what do exponential functions look like here? All right, so again, for convenience, instead of writing as f of x, and whenever we're sort of graphing them, it's a lot easier to just write a y in there. So y is equal to b to the x. But you can interchange f of x and y anytime you like. We talked about it when we did the graphing for the first time. Whenever you say f of x, remember you're saying that this graph fulfills the vertical line test, right? If you just say y, it could be that this guy does not fulfill the vertical line test. So it kind of just depends. Okay, but anyways, let's go for it here. So if we do not know how to graph anything at all, we can always make a table. Awesome. Jonathan got something. Jonathan learned something in the class here. This is good. All right. And we clap for him. Okay, so y is equal to 3 to the x. Here's what we're going to do. We're going to plug in a negative 3. We're going to plug in a negative 2. We're going to plug in a negative 1, a 0, 1, 2, 3. And just see what happens. See if we can get a good enough graph. All right, and this one we should be able to do by hand. So kind of let's think about this here. So 3 is the base, and we're going to take it to the power of negative 3. But hold on, the negative exponent means reciprocal, right? So this 3 to the negative 3 now becomes really 1 over 3 to the third. And I heard 27, you're right. 3 times 3 times 3 is 27, so plugging in negative 3 should give you an outcome of 1 over 27. Okay, can you do it on a calculator? Absolutely. Would I advise you to do it on a calculator? No, because then you get the practice of sort of working with exponents by hand. So, okay. 3 to the negative 2, that means, let's see, that means 3 goes on bottom, so 1 over 3 squared. And anybody, what is 1 over 3 squared? 1/9 is good. Okay, 3 to the negative 1. Cool, got it, 1/3. 3 to the 0. Ah, cool, now everybody says 1. This is better, a lot better here. 3 to the 1 power? Yeah, 3, cool, 3 squared? 9 I heard, yep, and 3 cubed. Whew, okay, yeah, notice some of these don't fit on the graph, but I wanted to at least give you a lot of points so we sort of see exactly what this graph looks like. Okay, so those of you with the printout from the match problems here, our graph only goes out to 5 each side, so I have to work in those confines here. So let's see, negative 3 maps to 1/27. So if I start at 0 here, negative 3, and I'm just going to go just barely up. All right, 1/9, again, negative 2, 1/9. I'm going to go just slightly further up, not by much though. 1/27 and 1/9 is a kind of weird ones to graph here. Okay, negative 1, 1/3. This one, negative 1, about a third of the way up, so about right here maybe. Okay, 0, 1, that's the easy one. There's that. Finally get some real numbers here. So 1, 3 goes up here. And 2, 9, whoa, that's all the way up there. I'm not even going to graph that one. All right, let's see if we can connect the dots. But notice this little sort of turn right here. It turns like this, and it gets closer and closer. My only question is this: does it ever touch the x-axis? No, not really, huh? The fractions will get bigger, or sort of smaller and smaller, right? So it'd be 1 over something, right? 1 over 1,000,000, 1 over 3,000,000 by the time it gets all the way over here. But notice it's never going to touch the x-axis. So the way you graph it, just kind of make sure you're just slightly above the x-axis as you graph it. And then you have this little turn. Once it's getting past the negative 1, then it's slightly bending, then it starts bending further and further, and it takes off. Cool, that is an exponential function graph. It's flat for a while, flat, and then at some point it starts going up. Cool, everybody got that one. Alright, let's do another one here. Again, slightly different. What happens if we change that 3 into a fraction? So I'm going to go with a 1/2. And it's kind of funny how the the example problems in the textbook sort of change. So for example number 3, in the text it was 2 to the x. And now you have the 1/2 for matched problems here. The match problem number 3, it was a 3 in the base, and now example 4 in the textbook is 1/3. So if you want to watch the math TV stuff, you'll sort of see a good comparison between the two. Okay, so let's go for it here. Again, plug in the same exact problems here: negative 3, negative 2, negative 1, 0, 1, 2, and 3. Just see what happens this way. Alright, so in Math 63, you're pretty much just introduced to the graph of the exponential functions. Not going to do that much with it. In Math 15, what we do is try to figure out faster ways to make this graph. Kind of like the same thing we do with parabolas. Just kind of, okay, how do I graph this faster? Alright, so let's go for it here. So 1/2 to the negative 3rd power. What's going to happen? Yeah, I got to take the reciprocal. Reciprocal of 1 over 2 is 2, right? And 2 to the 3rd power is 8. Are we good? Reciprocal of 1/2 is a 2. Negative 3 becomes a positive 3. And then we take the exponent rules here. So 1/2 taken to the negative 2 power. Reciprocal of 1/2 is 2, and we get ourselves a 4, and you kind of see what's going to happen here. Negative 1, which just means reciprocal as the exponent, which is just the 2. Alright, let's see if we got this here. 1/2 to the 0 power is? Cool, alright. 1 is good. Alright, 1/2 to the 1 power, of course, is 1/2. And then we have this little fractions happening here. So 1/2 squared. 1/4, yep. And 1/2 cubed. On a calculator, it'll be 0.125 as a fraction. let's see, isn't it gonna be 1/2 times 1/2 times 1/2? Is that right? So on top it's 1 times 1 times 1. On the bottom it's 2 times 2 times 2. Every k with 1/8. All right, can we graph it? All yours to graph it. All right, so let's see, -3, 8. Can't graph that one, it's off the graph already here. So -2, 4, now it can be graphed. -1, 2. 0, 1. Notice it's the 0, 1 was also on the previous graph as well. This tends to be a important point there. So 1 is 1/2, and then you go to 1/4, then you go to 1/8, and hopefully you can graph it here. Starts off high this time, sort of curves, and again, make sure you don't touch the x-axis as you go to the right on our graph. The book doesn't mention it, but the x-axis for these guys tends to be something called a horizontal asymptote, because it gets closer, closer, closer to that y equals 0, but just never touches it. That's for later on, though. Okay, so now the question is, how do all these things compare? Well, last time we did a base of 3. I want to see how does it compare to base of 2. What happens here? And there's a little graphic in your textbook here, which was useful. It's on page 496. And it just looks like this here. So if you say 2 to the x, what happens is it's sort of on this side, because the fractions don't go down as fast, the graph sort of goes higher faster when hey, that little center point, hey, look, all of them meet right over here. Then afterwards the 2 to the x goes up slower, right, because you're taking base of 2. The 3 is sort of like right in the middle. The 3 is in the middle. It's lower before the x-axis, and afterwards then, because you're taking 3 to some kind of power, it's going to climb a little faster. And then again, look at 4. Base of 4 is going to go underneath. They all meet here, but the base of 4 is going to go up faster as you put in positive exponents. That's what you sort of should see. So, so the higher the base, the flatter it is before this important point, and the faster it goes up after that point. If you have a fractional base, notice sort of like the same thing. It's like kind of like a repeat here. It's going to go down faster, and then until it gets to this point, and then it goes down slower afterwards. Okay, 3's in the middle, 4 again going down, and then there's a little switch that happens here. It goes down faster as it. Again, they're not touching the x-axis. It looks like it is, but they're really not. They're just very, 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 very close. Because by the time you get over here, 4 taken to the 4th power, whew, that's humongous. That's 1 over 256 at that point. This one is 1 over 64 over here. So, all right, just so you sort of see it. All right, another application of these exponential functions here, something called the compound interest. Did we talk about compound interest before? Maybe interest, yeah. Okay. Compound interest. A few little fun stuff like that. Let's see, Albert Einstein, as he was looking at numbers, again, brilliant mathematician, he said compound interest should be the 8th wonder of the world. It's just weird how things work out in compound interest. The backstory behind it is Benjamin Franklin, also kind of smart. He, when he was alive, he figured this out. He's like, whoa, that is so interesting. So what he did is he went straight to the bank and he deposited, I'm not sure what lump sum of money, and he says, I want this to be here for the next 250 years. And when the 250 years are up, I want this bank to gift whatever is in the account to the city of Philadelphia. Well, compound interest, it goes like this, right? At first it's very slow, right? The numbers are not increasing so much, and then after a certain time you get this exponential, humongous exponential growth in the money. And the reason for it is compound interest, what it does, let's say you had $100 in the bank. Let's say you get 10% interest. And so you put $100 in, year later, you get 10% of that money. So now you have $110. Good. The next year, you leave it in. Instead of getting interest on $100, you're getting interest on $110. So now you just got an extra dollar of interest. So like, oh, Mr. H, whatever, one extra dollar, who cares? But you're down here. You're getting this one, and then you went to here because you're getting a little bit extra interest. Eventually, you're gaining so much interest because that interest builds up on itself. So eventually you're now at, let's say, $200. Well, now that extra $100 that was in there originally, but now you're getting interest upon that other $100 of interest. We're good? So on that year, for $200, now you're getting $20. You've doubled your interest now. That is receiving into the account. And then after that, it goes higher and higher. Now you're at like $500,000, but you only deposited $100. So $500,000, 10% of $500,000. Mm-mm. 10% of $500,000. $50,000. So, yeah, if you have $500,000, you're still getting that 10% interest. But now, just that year, you have received an extra $50,000 into that account. We good? So, lo and behold, there's a new bank president that came in roughly 50 years later, after Benjamin Franklin deposited that money, and he looked at all the assets. He wanted to just take a look at all the assets, all the accounts, what's happening with the bank, and he noticed this one. He was like, whoa, what is this? So then he started calculating the interest. And let's just say Benjamin Franklin put in $100. And so, and we could probably even calculate it. That'd be kind of fun to calculate. Maybe during break I'll calculate it. So $100 in the account, let's say 6% interest or 8% interest at that point. 250 years later, it was somewhere in the trillions of dollars that the bank would have owed the city of Philadelphia. So lo and behold, the manager or the bank president said, no, stop. We're gonna cancel this account. We're gonna give the money that's accumulated over the last 50 years to Benjamin Franklin, and we're gonna close off the account because that's what interest does. All right, doing one more story, and then we'll go on to the math here. I taught the business finance class one time, and we were doing all this. It was like a whole semester, looking at simple interest, compound interest, something called annuities, bank notes. I mean, all the stuff that you sort of have finance stuff that you sort of put in money, lock away money, and you get money out. So it's kind of interesting. Rough estimates, ready? If you could put in $15,000 when you were 15 years old, anybody's still 15 years old, or are you less than 15? If you could put $15,000 into an account bearing about 8% interest, at 70 years of age, you should wind up a little bit over $1 million sitting in that account. Again, because of that interest building and building. But if you waited just 5 more years to do that, so let's say you started at 20. Cool. So again, this is a one-time deposit of $15,000, and you just let it sit there. If you waited until you were 20, you would have to pay $1,500 a month, every single month, right? So you can't let it sit there anymore. So you're going to be doing this every single month until you retire at 70. Good, does that make sense? Because of that last sort of interest. At the end, those last 4 years are earning so much interest. Like, how much interest on $500,000 is $50,000. Does that make sense? It's the interest all the way at the end that's accumulating so fast. Anyways, hopefully that was somewhat understandable. But let's see, maybe during break we can calculate Benjamin Franklin's deposit here. We'll see. All right, anyway, suppose you deposit $600 in an account with an annual interest rate of 6% compounded quarterly. Find the equation first of all. So here's our equation here. P is the principal. It's the amount of money you deposited. R is your interest rate. And N. N is the number of times that the bank is going to give you interest on your money. Now, most savings accounts, they are compounded quarterly. Most business savings accounts. So every 3 months, you get a quarterly statement from your savings account, and they add in the interest for that quarter, and they do that. You could have it compounded daily. There are some accounts that are compounded daily. There's some accounts that are compounded yearly. Most things are compounded monthly, though. Monthly is the sort of the norm. All right, anyways, let's go for it. So A of t equals, the original deposit is $600, and we get 1 plus interest rate, 6%, is that right? Yep, 6%. Write it as a decimal, so 0.06. It always comes in as a decimal, and n is the number of compoundings per year. So if it's quarterly, that means we have 4 compoundings in a single year. And then the exponent is going to be n times t, so it's going to be 4 times the t. All right, a few things. First, let's simplify this as much as we can here. So one of 2 ways to simplify. You can leave it just like this and simplify the exponent only, and that's fine. Most of the time, that's kind of how you leave it, because you want to be able to look back at the equation and say, oh, what was the interest rate I plugged in? Oh, how many years did I plug in? So this is a good way. As I've seen people practice finance and all that stuff, they usually sort of keep it like this, because all the information is still there. Okay, for calculating purposes, though, sometimes, yes, you just want to change it to a decimal and then simplify that base as much as you can. And then again, kind of depending what you're doing, what you're working with, if you care to see what was the original items here, or if you just need the base and that's it, just you'll write it either one of those 2 ways at the end. Got a couple people still finishing up writing here. Go for it. Okay. Part B. Now we're going to have to calculate it here. So all yours here. Can you find the amount of money after 5 years? Alright, all we got to do, plug in the 5 into this situation here. And again, depending which one you want to plug into, 5 times 4 is 20. So really what you want to plug in on a calculator, probably something like this. Alright, let you try it yourself first. Alright, again, I punched it in like this here, just to sort of see what I did. 600, parentheses 1.015, exponent is 20, and I got myself $808.11. Is that right? All right, and of course I got this little highlighter over here, which means a little something. The match problem answer, it does not match with what we got on the calculator here. So someone was half asleep when they were. Say again? I think it was like 806 or something like that. I don't know why. It was just off just slightly. All right. Okay. A little funny pet peeve of mine. Real quick here. Look at your dollar sign. Whatever you put in the dollar sign. Raise your hand if you only put 1 slash through the dollar sign. Raise your hand if you put 2 slashes through the dollar sign. Okay. Yeah, dollar signs do only have 1 slash. I don't know where the 2 slashes come from. I mean, I don't know. Is it just prove to yourself it's really, really a dollar? Is that why? I don't know. Okay. So this is more like the pre-algebra number crunching problem. This is what we do. We number crunch and we're done. Part C, Oh, and what I wanted to show you real quick is the other way. If you were to punch in 1 plus 0.06 divided by 4, again, a calculator that will do all the order of operations for you. Will actually do all that right there. Okay, good there. Jump to this one here. Now this one is more like the algebra problem, except we'll do it together here. Except we have no rules yet. We have no rules to actually help us to solve this problem. In fact, once we develop the rules, let's come back to this problem and we'll actually solve it. And so what the book does, it part C is mostly a calculator practice problem. It's more like a graphing problem here. Now that I'm thinking about it here, yeah, because let me see if quickly see if we need a graph. I didn't think we ever needed a graph on a calculator, but this one is true. Yeah, that's the only graphing problem. There's homework stuff where you have to graph this here. So the book talks about it as a graphing problem, and we'll see how that works. But first and foremost, let's set up the algebra equation here. So find the number of years it'll take to accumulate $1,000 from the original 600 that was there. So now in this case, A of t becomes the 1,000, and then you have the 600 here, 1.015 4t. So notice, hey, look at that. That's an algebra problem on our hands. So what should we do first? I heard divide by 600 in a very, very faint whisper. Okay, the zeros cancel off, so how about 10 over 6? 10 over 6 isn't that the same thing as 5 over 3? All right, this would be half of that, half of that. So 5/3 is equal to 1.015 4t. Okay, here's our little problem. Notice that this part right here, that t is actually in an exponent. And remember the rules from algebra way back when? It said the only time you can actually solve this type of equation is if the bases were exactly the same. If you remember that all the way from high school algebra. So we are stuck right here. We can't go any further than this. Oh well. So the only other way to solve it is you got to do it by graphing. And you know what? Let me think about this here. Those of you that do have a graphing calculator, I don't want you guys to go and buy a graphing calculator. Not for a single homework problem. Okay. How about this here? On the online homework, I'll give you guys full credit for this problem. If you want to try it, just to try it, that's fine. Okay, but this problem will receive full credit. There's an online, I'm sure there's an online homework question that's sort of like this. For the paper pencil homework, again, if you try it, but that's not one of those I'm going to look at to grade. Cool. So optional sort of homework problem. Wish all homework was optional, right? Okay, how do we solve this? We're going to try to figure out when this equation is going to give us 1,000. And so if you have a graphing calculator, raise your hand if you have a graphing calculator. 1, 2, 3. Okay, 3 of you guys. Again, if you want to follow along, that's fine. If you want to just skip the problem entirely, that's fine. But I just want to show everybody here how I would do this. Oh, you know what? Okay. So this guy here is the graphing part of the calculator here. And what we're going to do is we're going to type in 1,000, because that'll be... And then we're going to type in the other one here, which is 600. 1.015 taken to the, and then this one I need a parentheses as well here because I want to include the 4 and. Now I can't put a t in here because it has to be an x because that's the variable that the calculator uses, right? Because t, x, whatever, it's all dummy variables. You can plug in whatever you want. And then I'm going to graph it. Before I graph it, I just want to make sure that I am in the regular window, and we'll see Whoa, that's cool. I don't see a graph. Why don't I see a graph? Maybe it's because this is 0, 0, is that right? This is only going out to positive 10, and this is only going up to positive 10. And my graph, I know it's already at 1,000. We're good? So this is not a good window. I need to adjust my window. Okay, first of all, remember how we talked about quadrants? Do we even need these 3 quadrants? Or are we just really looking at quadrant 1, right? Quadrant 1 is what we're looking at. So forget the negatives. I just wanted to see positives. And then let's go, since we're looking at 1,000, let's maybe like go to, you know, maybe because 600 is what we're going to start off with, right? That's the deposit that we made, right? And as we go, eventually it's going to cross 1,000. So how about let's start off at 600 on the height, for our height, and then we'll go up to maybe like 1,400. Will that work? Or 1,200? We'll do that. And then number of years, let's go at 20 just to sort of see. We'll go at 20. So let's go on this particular calculator. You go to the window button and you can change all your window pattern settings here. So x minimum along the graph is going to be 0. Oh no, it's going to be 600. No, just kidding. That's the time, right? It's going to be 0. And we're going to go out to 20. Good there? And this little x scale, those are the tick marks that you see. Those little dashes that come down. So I'm going to go by ones. That's kind of good enough. You want to be about maybe 20 to 30 or so tick marks on the screen. The y minimum, that's the one I want to change. Y minimum is 600. And let's go all the way up to 1,200. Let's go double that. So I know 1,000 is going to be somewhere between there. Makes no sense to go by ones now for the tick marks. So let's go by 100 for the tick marks. That'll work. This one, no need to sort of think about this one. This is the resolution of x to y, or the scale from x to y scale, and we already changed it here, so we don't need this one. So let's now graph it here. So first of all is the 1,000. Hey, there's 1,000 coming across. There's my 600. Cool. So there's my $1,000. It reaches the intersection point is about right there. Okay, now I got to figure out the intersection point, and our calculator does this. Kind of fun. It has a little trace button on it, and you can, if you like, you can sort of trace along the, just when you sort of, hey, yeah, that's pretty close, isn't it? About right there. It's sort of like 5.5 years or something like that. That's what it says. X, y is 1,000. About 5.5 years, I would guess, if I was using the trace button. Your calculator also does, well, this calculator also does something called calculate, and it'll do some calculations based upon graphs. So this little yellow button is needed. Jump to here, and then you got something called intersect. You can find the intersection point between the two graphs. And so the first curve, it always kind of does this. Since this was y1, you click enter because you're trying to get the first curve. It's going to jump to the second curve already. So second curve, yes, I want this line. The only difference is if you had like 3 or 4 or 5 graphs at the same time. That's when you really want to choose between which graph you need. Anyways, then it says guess. What we usually do is we just go over here, we get closer to the intersection point, and press enter. Hey, cool, we were pretty close. 8.5 years, 8.6 years, somewhere right in that range. So 8.6 years. That's what I'll probably write down. If you wrote down 8.5, almost the same. So the graph should look like this. Here's my intersection point, and I don't care about the y value. The y value tells me the height. This time I'm more concerned with the x value. All right, and what the highlight on the PowerPoint means, the person that was working on the match problems still was very sleepy, and they did it wrong again. Okay. So far we've been looked at a base of 2, we looked at a base of 3, we looked at a graph of the base of 4, but there's a real special base that we use. And it's going to be a letter. It's called the letter E. and it's kind of like the number pi. Pi is a number that is like a decimal expansion, right? It goes on forever, forever, never repeats itself. Well, e does the same thing. E is a number. It's about 2.7183, and this number just sort of goes on forever, 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 forever. And so on your calculator, see if you guys can find this little E button. And it should be next to the LN button somehow. It should be somewhere next to the LN button, maybe the next button over, or it's the shift of the LN button. Alright, what is the letter E? Why do we use the letter E? Is because there was a famous mathematician, I believe French. His name was Euler. It was E-U-L-E-R. And he just did some awesome mathematics. He advanced mathematics quite a bit. Two generations removed from that, the person that discovers this sort of number that's out sort of in nature, that's what we call the natural number, and he finds it works so well with exponential functions here. It calculates things that we didn't think were possible to calculate, or makes a closer approximation. And so he dedicates this number, 2.7183, he dedicates to the famous mathematician of 2 generations ago, E, so therefore we're stuck with the initial of his last name for that number. Okay, so how do we write this? You can write y is equal to e to the x. You can write f of x is equal to e to the x, but it's e, and then you got this little x as the exponent. Usually what happens is if you press this button, the exponent, the caret key always comes up as well already, because you know you're going to have to take an exponent of it. So we'll sort of see that. Maybe I can show it to you now. Let's do that. So let's clear the screen here. Okay, so whenever I press this button, so notice if I just press a 4, it's just a 4. But if I put second in this, notice right away it's the E button right here. It already gives you my caret key or my exponent key, and it says, okay, what's the exponent? Because now I need to plug in an exponent for E. And E always needs an exponent afterwards. It's always E to the something. Okay, what does a graph look like? So if we approximate E to 2.7 sort of ish, so if you put 2.7 into here to take it to the negative 2 power, so it'd be 2.7 squared, and then 1 divided by 2.7 squared, it'll be approximately 0.135. Does that make sense? Again, doing this one here gives you that. E to the 0 is still 1. E to the 1 is 1, and there's your approximation. And instead of 2.7183, we usually approximate as 2.72. Sometimes if it's not that bad of an idea, you just put 2.7. Anyways, squared, cubed, and there's our function. What we should realize that the book doesn't talk about is this number should curve in between the 2 and the 3. Is that right? Remember? Let me go back real quickly here. Remember this right here? Remember the 2 and the 3 here? E to the x function should be like sort of like in the middle right here, a little bit closer to the 3. It should be right there coming through. So in between the blue and the green line, because the whole concept, it's a base of 2.7. So it should be between the 2 and the 3. Alright, now let's go on to this one. So where is this formula ever used anyways? One application is this whole concept of continuously compounded interest. So remember I said most interest rates are monthly. Some business savings accounts are quarterly. And sometimes compound interest is continuously compounding. A good example of it is, let's see, inflation rates. Inflation rates, you can't say the inflation rate here was this much, then this much, because inflation rates work on so many different topics. And so we don't think of inflation rate as jumping monthly. We think of inflation rate as happening every millisecond of every single day. And so that's why we need this little E. And if you put the base of 2 into here, it's too low. If you put a base of 3 into it, it's too high. It doesn't make sense. If you put this 2.7, like, whoa, cool. This works with the real world so well. So, kind of cool. So, inflation rates. And do we all know how inflation rates are calculated? There's a group of people. What they do, they are, I forgot what number there was. There's a group of people. What they do is they go across the U.S. and they'll just buy, or maybe not buy. They'll go in and they'll see how much bread costs. What's the average price for bread? And then they'll say, what's the average price for water? Whatever commodity is sort of the inflation indicator. And so I think it's 10,000. Can't be 10,000 items, but that'd be too much. But there's a certain amount of items that they use, and it's sort of staple kind of food: rice, potatoes. And so they'll average all those prices and they'll compare it to the previous month's prices, and then they'll draw a line, and there's your inflation rate. That's how we determine. So it's really the commodity of food. Is it going up or down? Anyways, too much information for this class. That was a freebie, okay? Not going to even charge you for it at all. Okay, suppose you deposited $600 into an account with the annual interest rate of 6%. Now it's compounded continuously. So if you made that agreement with the bank, then it's every single millisecond they're going to give you a little tiny bit of interest. At this point, yes, you do need a computer system to calculate that. Some kind of banking software is going to do that for the bank. I don't think they're going to have one person there every single second. It just doesn't make sense. All right, so let's go for it here. So A of t, let's get the formula first. Principal was 600, E, and the R, sorry, not the R, it's, yeah, the R, sorry, the rate times the time. There it is. Simplifying that a little bit further, just so we got it, so 600 e to the 0.06t. We don't really need that little parenthesis here. That's kind of cool enough. And again, you probably will need a calculator to do this here. As we plug in a 5 goes in. It's 600 e to the 0.06 times 5. And if you want to simplify that a little further, how about e to the 0.3? Just multiply the exponents, the product of the exponents here. At this point, yep, I need a calculator. And anybody with an answer. All right, and plug it into the calculator here. All right, those of you that have a calculator, you do have to find the E button. If you don't find it, I'll help you during break here. But I got myself $809.92. All right, jumping to 8.2, we're good? Okay, so that was the exponential function. We learned how to evaluate it, plug in numbers with the calculator, graph it, some application sections in here, and our problem. Our problem is that we cannot solve this algebraically yet. So we have to deal with some rules here. So 8.2 is sort of theoretical mathematics a little bit here. 8.2, we're going to look at theory for a little bit, and then we're going to jump into 8.3, which we apply the theory to what we really need. But we need to understand something. We understand something called the inverse of a function. What does an inverse of a function do? As an illustration here, it's just going backwards. So on the diagram, figure 1 shows the route, or the route, whichever one you like. Justin takes to school. So home is right here. He leaves his home and drives 3 miles east, turns left and drives 2 miles north, and he's at school. On the way back, the reverse is true. So he actually has to redo his steps. So now it's 2 miles south. We're good. He takes a right-hand turn instead of a left now, and he travels 3 miles west, and he arrives at home. So it's really undoing the process that you did. Easiest example, if you're adding 4, what would be the inverse? Hey, subtracting 4. If you're dividing by 12, inverse would be multiplying by 12. That is what the inverse does. Right, in terms of a graph though, let's jump to this. This is also in your textbook here. So if we think of the route is one point is home and the other point is school, and that's the way we traveled. If he's traveling backwards, then we think the first point was school and the last point was home. We're good? So here's what we do. What happens in an inverse function? It's the input gets switched to the output. So 1, 4 now becomes 4, 1. And there's your inverse operation. Okay, 2, 5 becomes 5, 2. And so on and so forth. Notice we're just switching the x and the y. And so in this point, I kind of wanted to say this here. So what is f of 1? Anybody? What is f of 1? 4, right? And then you say to yourself, okay, what's g of 4? It's 1. Notice it just reversed. It did all the work that it did before. So the f of x, anybody know what's the formula for f? What are we doing? How does 1 go to 4, 2 go to 5, 3 goes to 6, 4 goes to 7? What's the relationship between x and y? Yeah, you're adding 3 each time, right? That's all you're doing. What are we doing in g? Subtracting 3 each time. Cool. Okay. That's what it is. So the inverse operation is what undoes the work of the previous function. How does it work? So we saw how it works in terms of points. Now let's see, how does it work in terms of a formula? So number 1, f of x is equal to 4x plus 1. And again, each of these are just one of each type. That's all we're going to cover. We're going to see how does it look in terms of a formula, how does it look in terms of a graph. All right, so let's see if this makes sense here. On the previous slide, we learned that what happens with inverse function is the x coordinate switches with the y coordinate, right? So instead of calling this a function, we're going to just call it just a plain old graph. How do we say that? How do we say instead of this is being a function, this is just a graph? Perfect. Y is equal to 4x plus 1. Awesome. There it is. It's a plain old graph now. So if from the previous slide we know that the x coordinate changes with the y coordinate, how about let's change the x variable and the y variable? So if coordinates change, that means variables can change, because that's really what we're doing. Now the question is, can you solve for y? That's it. Alright, subtracting 1 looks like, because I'm trying to solve for y again here. There's 4y, divide by 4, is that right? And on this side, I've got to divide the whole thing by 4. So how about x minus 1, sorry, divided by 4 is equal to y. Switch it around, because I like my y variable on the left. And voila. There is the equation for its inverse. And we should also see something as well. So notice on the original function, look at this here. What are we doing to x first of all? We're multiplying by 4, is that right? And then we are adding 1. Notice what we're doing over here. It's not only the operations, but the order is reversed as well. So what are we doing to x now? Subtracting 1 and then dividing by 4. So it's undoing really the work. Another way to see it is just to plug in some values here. If I were to plug in a 2 into here, let's say 2 times 4, 8 plus 1 is 9, right? Plug in the 9 into here. 9 minus 1 is 8. Divided by 4 gets you that 2 back again. It's almost like you didn't do any work at all. Okay, so that's the equation aspect of it. Let's go to the graph aspect. What does a graph sort of look like in that? So find the inverse of y is equal to x squared plus 1, and then graph the function and its inverse and see how they compare on the graph. All right, find the inverse. I guess we're going to do that first. All right, hopefully, let's see, switch the x and the y first, and let's solve for y. Subtract 1 from both sides. Ooh, this is an interesting one here. What should we do here to solve? Square root both sides, yep, and then we have to put this little plus or minus, don't we? So this becomes plus or minus x minus 1 is equal to y, or turn it around real quickly here, it's plus or minus square root of x minus 1. All right, we should realize something. We should realize, if you look down here, is this a function? Anybody, yes or no? Or we'll take a vote here. I'm going to say, Mr. H, this is a function. It's cool. Scared to raise your hand. Okay. I say, Mr. H, this is not a function. And I know why. Nobody. Okay. Remember what happens with the function? Function says this: if I plug in a number, I should get out a single number, right? So if I plug in a 2, I should get out a 9. If I plug in a 7, I should get out a 12, right? There's a correspondence of one number to another. So over here, if I plug in, I'm going to choose a very specific number here. If I plug in a 5 for the x, how many numbers will I have out? So 5 minus 1 is a 4, right? Square root of 4 is a 2, but then I have a positive 2 and a negative 2. So for a 5, the answer is 2 and negative 2. And that's not a function anymore. I can't have one number plug in and a totally different aspect than the other. Another way to say it is a function says, if I say a number, you guys will all say the exact same output number, right? Let's say we have a function, I say 2, and then everybody says 9. That's called a function, because everybody's saying the same thing. This one, if I say 5, some of you guys say 2, some of you guys will say negative 2. That's no longer a function. Okay, so let's see. So I got this. I have the inverse, but the inverse itself is not a function. That's what we've got to understand here. Okay, now, jumping to the graph here. Can anybody graph for me x squared plus 1? Ooh, it's a parabola, I think. And then maybe in your mind, just kind of plug in a few numbers just real quickly here. Plug in a negative 2, see what happens. Plug in negative 1, plug in a 0, plug in a positive 1, positive 2. Okay, so in my mind I sort of plugged in a negative 2. Plug in negative 2 would make a 4. 4 plus 1 is 5. Plug in a 0, even better. How about a 0 down here? It will give you me a 1 as my output. Plug in a 1 into that. 1 squared is 1 plus 1. Everybody okay with 1, 2? Plug in a 2 would give me a 5, and then plug in a negative 1 gets me a 2, negative 2 gives me a 5. All right. So this is the original function, y is equal to, or the original graph, y is equal to x squared plus 1. Everybody good there? All right, now I got a little problem over here. I can plug in values into this as well, right? I can plug in a 2, I can plug in a 7, but they're kind of hard to do that. Hey, you know what, real quick here, before we do that, let's think of this here. Remember how the inverse function is really just the switch of the x and the y, isn't it? Well, I have right here, what, 1, 2, 3, 4, 5. I got 5 points here. Can't I just switch the x and the y right here? Like this right here, 2, 5. What would be the inverse coordinate of 2, 5? We don't switch the sign, we just only switch the coordinates. So I need the inverse coordinate of 2, 5. Nope, not there yet. Let me jump to this here just to make sure we got it, because I would hate to not get this correct here. Let's jump to this. Remember, this is your function, this is your inverse. What's happening with x and y coordinates? They're just swapping. So positive 2, positive 5, this coordinate here, what's the inverse of that coordinate? 5, 2. So go here, 5, 2. There's my coordinate of my inverse graph. We good? Okay, how about 1, 2? Hey, 2, 1. So the graph's right here. Okay, 0, 1. 1, 0. Okay, negative 1, positive 2. 2, negative 1. So it's down here. And last one here, negative 2, 5. Would be 5, negative 2. Good there? All right, can we connect these guys together somehow? I think so. Something looks like this, is that right? Again, we're looking at inverse function, but in a graphic form. Cool. On the previous slide, we looked at it in an algebraic form. This is a graphic form. So my original graph, my inverse graph. If my x's and y's switch, this is kind of funny. Notice if they're in the first quadrant, they actually stay in the first quadrant, right? Because both of them are positive. Right? Look at that, positive. It was on the y-axis, now it's on the x-axis. So it's kind of funny how these two just sort of they map this way. They map sort of diagonally, don't they? And so in the book it talks about this here. There is symmetry here, and the symmetry is like this right here. The symmetry is actually on this line right here. And sometimes the line is drawn, sometimes it isn't here, just to show you, okay, if this graph is here, if we were to fold our x-axis diagonally along this line, would fold it over, the red graph would be matched up with the blue graph. Does that make sense? So there's my inverse function. Actually, no, there's my inverse graph. Is the blue line actually a function or no? Hey, no, it actually does not pass the which test? So it's the V. Yeah, the vertical line test, right? The blue line does not pass the vertical line test. This guy's not a function. Is the red line a function? Yeah, the red line, yeah, absolutely. It passes the vertical line test. We could have wrote f of x is x squared plus 1. Okay, we good? So hold on. Question, Jonathan? Again, some abstract stuff here. The question is, will we have to graph both on the test or just one? Let me pass out the study guide and we'll see. Okay, so now I got a little question for you, real quick here. The red line does pass a vertical line test, is that right? But maybe, you know how we switch the x and the y's? Right? This guy does not pass a vertical line test. But hold on, if these guys are switching x and y's, I got another little test. it's going to be something called the horizontal line test. Because x and y switch, does the red line pass a horizontal line test? Okay, so here's what we know. Kind of be very, put your thinking caps on real quick here. Ready? If a graph does not pass a horizontal line test, the inverse of that graph is not a function. Good? I'll say it again. Ready? If the original graph does not pass a horizontal line test, the inverse of the graph is not a function. Cool. So let's do it kind of both together here. If it passes, the vertical line test is all about the function, the graph itself. The vertical line test is talking about the graph itself. When we do that, we say, okay, is this graph a function or not? The horizontal line test is actually now talking about whether the inverse is a function. Cool. So there's those two things here. Okay, this is in your textbook here. I'm going to just kind of run through the pages here. Let's do the definitions here. So if it passes a horizontal line test, it's called a very special function. It's called a one-to-one function. So a one-to-one function is a function that passes the horizontal line test. And if it passes the horizontal line test, that means the inverse of that graph is also a function. Question?
So if it does pass a horizontal line test, how would that look? Would the parabola be in the first quadrant?
A question about the parabolas here. I will real quick say no parabolas will pass a horizontal line test. Right? Because parabolas go down, right, and they turn around at the vertex and they come back up. And so that's our problem with parabolas. These guys will never pass a horizontal line test because there's symmetry. But let's go to this. This will be good. Oh, sorry. Let's go view all. Let's go to here. My question to you is this little function e. Does this pass a horizontal line test? No, back up a little quick here. Does this pass a vertical line test? It passes a vertical line test, right? Comes down like this, boom, boom, boom. That means that this guy is a function. I could put f of x right here. Good. Does this pass a horizontal line test? No. Ooh, let's talk about it. At 5, does it pass? Yeah. Yes, passes. Yes, passes. Yes, yes. Now over here, again, it's going down, down, down slowly, right, as it goes to the left. But it will always pass a horizontal line test, right? Because there's never a time where it's going to come back up. Because when it comes back up, then it's not going to pass. So we know that whatever, if we were to graph the inverse of this guy, we know that that inverse graph would itself be a function. We're good? Let's jump to another one here. Let's jump to the one that we did over here. On 3. Okay, yes or no? Does this pass a vertical line test?
Yes.
Is it a function?
Yes.
Yes. Does this pass a horizontal line test?
Yes.
A horizontal line test, coming straight down like this. Coming straight down. Again, this was going to go down slowly, but it will forever pass a horizontal line test because it never comes back up. It never goes back up over here. So, does it pass a horizontal line test? Yes or no? Yes, it does. Is the inverse of this graph also a function? Yes. Okay, cool. Again, I gotta do it because it's sort of abstract stuff, and abstract stuff has to sort of sink in slowly. Okay. So let's go for it now to the definitions here. A function is a one-to-one function if every element in the range comes from exactly one element in the domain. That's a good way of saying passes the horizontal line test. All right, so would F pass the horizontal line test? Yeah, it will not,
2, 3, 9.
because you have repeating y values, right? See, this is the repeating y value. There's a 3 here, there's a 3 here. So x being 2 maps to 3, x being -1 maps to 3, and we got a problem, because when I start coming down on the horizontal line test, y equals 5 passes, y equals 4 passes, y equals 3, and I don't think so. So let me draw it for you. Alright, so let's go for it here. I'm going to just graph these individual points, because notice they're not connected, they're just individual points. So 2, 3 is right here, -1, 3 is right here, and 5, 8 is over here. So that is not going to pass a horizontal line test right at y equals 3, because it's going to hit both of these points. So no, this guy does not pass a horizontal line test. And what this means is that every element in the range, it means that this guy here comes from the exact same element in the domain. So there's no repeating of y values. Okay, over here. And we should see it on this graph as well. Let's go back over here. Do I have repeating y values? Yeah, right here. Look at that. 2, 5, as well as -2, 5. Notice the 5s repeat themselves. So this guy is not a one-to-one function. Okay, g. Is that a one-to-one function? Do I have any repeat of my y values?
No.
So 5, 7 is somewhere over here. 3, -1 is somewhere down here. And 4, 2 is somewhere over here. So this guy will pass the horizontal line test, no problem. Okay, so now let's go to the horizontal line test. That's on the textbook as well. And that's what we've been talking about here for a while here. Talking about the whole concept of if a horizontal line crosses the graph at a function in more than one place, then the function is not one-to-one, because the points will fail the horizontal line test. Jumping to notation here. Functions whose inverses are also functions here. That's what we're going to talk about here. So if I have y is equal to f of x, and I know this guy's a one-to-one function, so then I'm able to calculate the inverse. I gotta say, hey, the inverse of this guy is also a function. I gotta say, hey, that's gonna be a function there too. So the notation for inverse is we have a little -1 right here. So -1, you can't say exponent, it's not an exponent. It's just that is the notation for inverse. Kind of funny. In mathematics, we sort of run out of symbols, right? Let me do this here. If you see this right here, what does this mean? That means, right? That means -1. Is that right? Okay. How about if I do it like this? 3 to the negative. What does that mean? In fact, let me go to this one here. This little negative right here, it means opposite, doesn't it? I'll even do it like that. Could mean opposite of 1, or it could be -1, just depending what you're really trying to say at that point. Or it could be also subtract 1, which is a little different. Oh, time to wake up. Okay, 3 to the -1. Oh, phone. Oh, there we go. We'll wait for the lovely music to stop here. We're good. Okay. 3 to the -1. What does this -1 mean? Yeah, what's that called though? What is that? I'll help you. Ready? It starts off with like recip and it ends with percol. Right? Isn't that funny? This -1, if it's inside the exponent, it doesn't mean -1. It doesn't mean opposite of 1. It doesn't mean subtract 1. It actually means reciprocal of the base, which is totally different than saying -1. Now, if I write it like this, good. If I write it like this, what does that mean? Okay, we good there? So if a negative 1 is by itself, it could mean one thing. If the negative 1 is in the exponent of a number, it means reciprocal. If the negative 1 is sort of like in the exponent position of a function, then it means inverse. So the same symbol, whole bunch of different usages. Okay, let's go for it here. So find g of x, or if g of x is that right there, find the equation of inverse. We've done this before. I'll start it off for you guys, see if you guys can finish it off by yourself, because you guys are sophisticated Math 63 students. You guys should be able to know this. I'll give you a hint, something about factoring as well, so just sort of leave that in mind there. Okay, so we've done this before. How do we find the equation of its inverse? Instead of g of x, it's going to be just a simple y. And what do we do next? Sorry, I heard it almost. Swap the variables. Yep. Cool. All right. Can you solve for y? That's what I want you guys to do there. Solve for y. All right. I'll give you a little bit of time. Try it yourself. Hopefully, you tried it yourself here. Let's see what we got here. Hopefully, do this here. You multiplied by y plus 1 to get rid of any fractions. You do have to distribute the x this time, because the x has to go to that and that. So xy plus x is equal to y minus 3. Yes. And how about I'll let you guys actually see it. Okay, a lot better this time. So great when you can see the screen. Okay, so y plus 1 on both sides. The y plus 1's cancel here because that's exactly what we want. No more fractions. Love it. So now the name of the game is, can you get y's all by themselves on one side? So let's subtract the x's first, and let's subtract the y's, because that'll make the y's cancel from here and go to this side. We got a little problem. xy subtract y, those are not like terms. So I got to write them separately. xy minus y. The x's are gone here. The y's are gone here. And this time, kind of depending how you want to write it. You can write negative x minus 3, negative 3 minus x, whatever you want to do on that one. Okay, how do we solve for y? Factor out the y. You got y in here, y in there makes leftovers of x minus 1. And final answer, divide through by x minus 1. And voila, I have y equals negative x minus 3 over x minus 1. Again, it could be negative 3 minus x on top too, it doesn't matter. Okay, and here's my only question. Dun, 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 dun. Is this a function? So my little question marks here. We'll answer in just a second here. So my question is, can I write this or no? Can I write, oh, g of negative 1, or inverse of g of x is, am I able to write, whoa, sorry, am I able to write that down, yes or no? Well, got some yeses. What do we have to do? We have to go back and prove that this original function passes what test? We've got to prove that x minus 3 over x plus 1 passes the horizontal line test. If we can prove it, then we can say, oh, this guy is g inverse of x. Cool? So that's why you have a graph on your match problems here. There's a graph next to 3, and like, hey, why do we do that when it doesn't say anything to graph anything? So let's go for it. Let's make a graph now on the side here. Now, we made graphs of these before, is that right? It was at the tail end of chapter 5, I think. Okay, quick recap. How do we graph? This is called rational functions here. How do we graph rational functions? Well, no, you guys forgot? You serious? Let's go for it. So how do we graph rational functions? This is what we do. We take a look at our denominator and we say, what can x not be or else it causes a undefined term? -1. That is going to be our vertical asymptote. We put a slash down all the way like this. Boom. Right away. Alright, next. We have a vertical asymptote. And if we remember this one from when we did this here, I'm sorry, there isn't my vertical asymptote. Sorry, we have a horizontal asymptote. The horizontal asymptote is the division of my leading terms right here for these type of functions. Once you get to Math 15, we're going to look at different rational functions, but these are the easy ones. So what is x divided by x? 1. So my horizontal asymptote is y equals 1. And again, we did this in 5.6 when we did sort of the application section. One of the applications was we can now graph these rational functions. Okay, so we get our vertical asymptote, we get our horizontal asymptote. Next is we need to find maybe a point, maybe 2 points, whatever. So how do we do this? We plug in a 0 for the x and then just see what happens. If I plug a 0 in for the x, that's going to give me my y-intercept, is that right? And then I can get the x-intercept. Let's do the x-intercept first. How do we figure out the x-intercept? We look at the top equation and the question is, what would produce a 0 on top? 3. Bam, done. There's my x-intercept. So what makes the 0 on top would be the x-intercept. The y-intercept is us plugging in a 0 in for the x. So 0 goes there, 0 goes there. What's the grand result of all this? -3. There's my y-intercept. Now, based upon those two those two asymptotes, those two intercepts, can you graph the equation? Oh yeah, sure. The question is where to get the -3 from. If I were to plug in a 0 into the x here and a 0 into the x here.
Oh.
So the way to get the y-intercepts is you plug in a 0 in for the x. Alright, there's only one way this graph can flow. If it never touches the vertical asymptote, it has to go through these 2 points. So if it goes through these 2 points, that means the graph has to start here, a little bit higher than the horizontal asymptote, and sort of curve before it touches the vertical asymptote. The reason I know it is because I have to go down here, because there's a split right here, and I have to go through these 2 points. Interestingly enough, my question to you guys, is this passing a horizontal line test? That's what we're trying to get to. Alright, let's go show of hands here, of course. You gotta vote. I'm going to say, Mr. H, it does pass the horizontal line test, Mr. H. Jonathan, is that a raising of hand or no?
Yeah.
Okay, cool. 1, 2, 3, 4. Late bloomers here. Okay, 5, 6. Okay, 6.5. I'll count that as a half. I'm going to say, Mr. H, it. What's the next one? It does not pass the horizontal, Mr. H. I'm confident. No takers. Okay. All right. So let's go for it. Putting a horizontal line like this, coming straight down. It's passing, right? So far passing. So far passing. Just like remember those exponential equations. Remember that how this was going to come down across here, right? It's going to get lower and lower and lower to this horizontal asymptote, but it's never going to touch it. So yeah, this graph here passes the horizontal line test. Going on this one's also going to pass the horizontal line test. Again, it's climbing up to the y equals 1, but it's never a time where it actually turns around and goes back down. That's when we have problems. We have problems when there's parabolas. Parabolas are problems because then they turn around. So yes, this one does pass the horizontal line test. So Here it is. Let's see if this makes sense. It passes the horizontal line test. Check. And let's do the logic here, okay? Logic and steps here. Since it passed the horizontal line test, we know that this is a one-to-one function. Yeah, exclamation point. All right. Cool. Okay, because it's a one-to-one function, what else do we know? Okay, let's see. What do we know about the inverse?
We know it's a function.
Awesome. There it is. There's the logic. The inverse equation is itself a function. So go back to what we were doing here with number 3. Can we erase the question marks? Or no? Yeah. Going back to the question number, what we were doing previously with this, we erased the question marks, and now the final answer is g inverse of x. That is the final answer, because we say, oh, look, we found the equation, and we found that the equation itself is a function. All right, number 4, last one for this section here. So we want to graph y is equal to 3 to the x. Then we want to graph its inverse on the same axes. Hey, we already graphed 3 to the x. Remember, maybe a little chart. Remember how we made a little chart like this? So either go back to the problem when we graphed it, or you kind of just sort of quickly think in your head, okay, what are the points we used? Again, go back to notes, probably be the best. Go back to notes. It is 8.1, and it is question number 3. 8.1, question number 3. All right. I'll even be generous here. I'll go back to it as well. And we did something looks like this, is that right? So 1/27th, then a 1/9, then a 1/3, then a 1, then a 3, then a 9, then a 27. And the graph, again, we need these points right here when we're going to be looking at it. All right, graphing that, and then after that you do that, can you graph the inverse? Alright, and there's kind of 2 different ways to graph the inverse. Let me jump to where we're at on the problem here. So there's my dots. There's a -3, 1/27th, -2, 1/9, -1, 1/3, 0, 1, 1, 3, and then that's about it. So kind of 2 different ways. You could use the table if you like, and make another table, and just sort of reverse the order of the x and the y's. That's easy enough. You can just kind of take these points and just kind of plot them. So this is kind of fun to plot here. -3 and 1/27th. Can you plot for me 1/27th common -3? So we go from the origin, right? We just go just a slightly a little bit, and then we're going to go down 3 units. Good there. Then we're going to go, let's see, -2, 1/9. So now we're going to go 1/9 down 2, so just a little bit off the y-axis. -1, 1/3 now becomes 1/3, a third of the way, and down 1. Good there? Okay, the easy ones, 0, 1 becomes 1, 0, and 1, 3 now becomes 3, 1. And bless you. All right, and connecting the blue dots together, there's my inverse graph. And let's see, my question, trivia question is the blue line a function? Absolutely, yep, because this guy passes the horizontal line test, right? Because it goes down further, further, down, 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 and it will always be able, it doesn't come back up. So notice also, remember how we talked about this being a horizontal line test for the red line? This becomes the horizontal line. I'm sorry about that. Not horizontal line test. This is a horizontal asymptote, right, for the red line. Kind of funny. For the blue line, this becomes a vertical asymptote now, for the blue line right here. All right, and some kind of weird thought. Isn't it kind of interesting? The red line, right, as it goes off to the left, it's able to go forever lower and lower and lower and lower, but never pass a certain predetermined point, right? Kind of sort of weird, sort of boggles the mind a little bit when we think about that, right? So this guy forever decreasing, but never getting to 0. Kind of fun. Now sometimes we have these weird infinities that are actually built into finite space that we create. All right. But are there actual infinities, or this is just a theoretical infinity? I know. That's when we stop. That you ponder that philosophical question here. All right, so that is the end of 8.2. The only, oh, sorry, one small little thing here. I wanted just to put this in here, like we did last time. Remember, these two are symmetric about this line right here. Do you have to draw it in? You don't. But just to sort of just at least show you, there's symmetry here between the inverse and its graph. And one more little thing here. There's a little summary in your book at the end of 8.2, and maybe if you just want to refer back to it, maybe the best thing to do it. Anybody got the page number?
507.
Awesome. I'll go with that here. So page 5. I'll go to page 507. It'll be sort of a good summary, just sort of keep things correct in your mind here as you think about it, that's all. Let's see if this writes correct. Nope, it doesn't. So 507, how about that? We'll just leave it as 507.